Okay. Hello, everybody. Let's start with section 2.2. So we finished 2.1. Which was talking about just functions. Defining the definition of a function. We talked about domains of a function and how certain functions have restricted domains. In particular, the functions with x in a denominator and x under a root, like a square root, have restricted domains. And we also talked about different ways to represent functions verbally, algebraically, numerically, and graphically. And I do have some problems for you to mark for review. I'll give those to you at the end of the lecture. Okay, so let's start 2.2, which is graphs of functions. So let's dive a bit more into this graphical, well, one second. There we go. Graphical representation of functions, graphs of functions. Okay, so if you read the book, they give you this fancy definition for the graph of a function. It says if f, and we're going to parse through this. So if f is a function with domain A, capital A, okay, then, so A is just representing some set of numbers, okay? It's probably an interval, right? And for most of our functions, the domain is just the entire real number set. In fact, it's so inclusive that we often don't even we'll stop mentioning it for a lot of functions because its domain is just everything, all the real numbers. But here we're being very specific, and a definition being very specific. Then the graph of f is a set of ordered pairs, in other words, coordinate points, so ordered pairs are coordinate points on our xy plane, or on our, Cartesian coordinate plane. And here comes the set. So remember, set is denoted by a curly bracket. And if you don't know that, that's okay. So the ordered pairs, you would expect me to write x and y, but I'm going to write x and f of x because those are the outputs, right, from a function. Its input is x and its output is f of x, such that x needs to be in the set A. The set of ordered pairs, this stuff, plotted in the coordinate plane. Yeah, that's fine. In say the coordinate plane. All right, that is all very fancy talk for saying the graph of a function is just a collection of dots. It's just a collection of dots at specific points defined by whatever the function is. Okay, so in layman's terms here, the graph of a function is a collection of dots and there's infinitely many dots, right, on the graph of a function. Well, at least for the functions we'll be graphing. There's going to be infinitely many dots. So how do you show like infinitely many dots on a picture? Well, we just connect it with a solid line that we connect or represent with a solid line. Collection of dots that we connect with a solid line. You know what? Yeah, I'll just leave it at that. I mean, can get more detailed, but I mean, one of the things, in math is when you learn a new definition or theorem or idea, you really understand it when you can as I say it in layman's terms. In other words, like if you could explain this to a child, right? Take this thing, this if f is a function with domain A, then the graph of f is the set of ordered pairs, and this little thing plotted in the coordinate plane. That's a lot. That's like a mouthful, right? Just to say it's a picture, right? It's just a picture of a function. And where does the picture come from? Well, it's like a line. It's some line, maybe a curved line, and it's just infinitely many dots. Where do the dots come from? Well, they come from whatever the function is telling you to do. So let's jump straight into some examples of this. And what do I mean when I say whatever the function is telling you what to do? Well, remember, a function is a rule that takes in inputs, does something to them, and outputs new values, right? So that's what I mean by what the function tells you to do. Let's get straight into it. Example 1. We've already practiced evaluating functions at particular values. That was training for what we're about to do here. Sketch a graph of the functions by plotting points. Now, we've already done this back in section whatever it was for equations in 2 variables. Maybe it was 1.2. Yeah, anyways. Yeah, graphs of equations in 2 variables. That was section 1.2, where we graph things like y equals x squared. It's going to be pretty much the same, except now we're calling those things functions. We're calling that x squared thing a function, and we're also going to broaden the different types of functions that we're going to try to graph. We're going to try and graph more things now. But let's start off with that classic example, f of x equals x squared. Now, we know from prior experience that a good set of values to graph, or to plot rather, for this function, so x here and f of x here, are the whole number, or rather the integers between -2 and 2. Those 5 values. Okay, so this is, remember, evaluating a function at a particular number, so I'm literally plugging -2 in for x, so that gives me 4, right? -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1 again, and 2 squared is 4 again. So we're seeing like a symmetry here. And that's reflected in the graph. That symmetry we see in our table of values is reflected in the graph here. So if I call this x and this, I can, yeah, I'll just call it y. I could call it f of x or whatever I wanted to call it. We'll call it x and y. If I graph these points, let's see, -2, 4. So -2 is here, 4 is up here, right? Got to know how to graph points. -1, 1, -1 is here, and then 1 is there. For my x, y, 0, 0, that point's easy to find. That's right at the origin. Then 1, 1, +1 for x, +1 for y, and 2 for x and 4 for y. There we go. So it has this general shape. Now, all right, back here I said the graph of a function is a collection of dots that we connect with a solid line. So did I really graph enough points for you to completely be convinced that this is the shape of the x squared graph? Well, that's, you know, that's kind of debatable, right? Maybe you're not convinced. Maybe you want to see like what's going on in between, right? What's going on between 0 and 1, or between 1 and 2, or beyond 2, right? What's happening at 3, 4, 5, 6, 10, right? You know, there are infinitely many points here. Even just between these two, any little segment of this, there are infinitely many points stuffed there. So are we really sure that this is what's happening? Well, yes, because we should, at this point, we should all start to become familiar with what an x squared graph looks like. It's got this nice, it's called a parabola, parabolic shape to it. And a lot of what we're going to learn in this section is going to be having a function defined algebraically and then just immediately remembering what it looks like without having to graph tons of points to be convinced about what it looks like. Now, in this first step, in this first example, we are going to graph a bunch of points for each function that I'm telling you about so that we can start to become familiar with their shape. And so you see where it comes from. But eventually, when I say, you know, if I tell you to graph f of x equals x cubed, you know, you should just be able to immediately call that general shape to mind. All right, speaking of x cubed, let's graph that one. Let's see what that looks like. So we'll call this part B. Let's say f of x equals x cubed. I'm going to draw my graph over here. Oops, over here. I'm going to need, if you're graphing along with me, you probably want a little bit more space on that y-axis, just so you know. So I'm going to make my tick marks smaller in this case. So 1, 2, 3. And let's go out to 8. You'll see why I'm going out to 8. You know, sometimes this stuff where you're graphing functions for the first time, you know, maybe it's hard to know how big to make your graph, right? That just comes from experience, and also I'm telling you, right, to help you out so you don't have to redraw the graphs in your notes or anything. All right, so let's make our table of values. We've got x, we've got f of x here. So this is a new, right, this is a completely separate function here. So let's pick the same numbers, -2, -1, 0, 1, and 2. Okay. Now, Aviana, what would -2 cubed be? Okay. All right. Let's see. How about Maya? What would -2 cubed be?
I can't see nothing. I just see the graph.
Oh, is yours frozen too?
Yes.
Okay. Let's wait. Nikita said hers is frozen too. I guess let's wait a second. Maybe campus Wi-Fi is messing up. Let's give it a second. Let me check my Wi-Fi. Okay, my 5G is working. Well, let's see what to do. Yep. I'm just gonna go ahead and fill this out and.
Do you still want me to answer it? I see it now.
Oh yeah, good. Yeah. So what is -2 gonna yield when I plug it into x cubed here?
It'll be -8.
Yeah, good. -8. -8. And then when I plug -1 in, I get -1. And then 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So I'm seeing another like sort of symmetry again, but this time the negatives that I inputted into the function outputted a negative. So in part A, the negatives that I inputted for x, the function gave back positive values. So this one gave negative values. Let's see what that looks like. All right, so -2, -8. So -2 for x, and then all the way down here at -8. You see why I made my tick mark smaller so I could fit that -8 and 8 on the vertical axis. Then at -1, -1, that's here in the still in the third quadrant. Then we go through 0, 0, and then we hit 1, 1 right there, and then we hit 2, 8 all the way up here. So that's all 5 points there, and then connecting them with a nice curved shape there. There we go. That is the general shape for x cubed. That is the general shape for an x cubed graph. All right, part C, let's make some observations about the graphs in A and B. In fact, I'm going to say this. What does the exponent on x tell us about the graph? Now, to answer this, I'm going to share my screen and hopefully it works, the Wi-Fi and everything. And we're going to go to desmos.com, which I believe I told you all about last time. Let's see. Is it sharing my screen? Nope. Hang on. I think I shared the wrong window. There we go. All right. So Desmos. Okay, can you guys see this graphing calculator window?
Yes.
Okay, thank you. Okay, so here it is. Here it is. Let's look at, let me zoom out a bit. Whoa, not that much. There we go. Here is x squared. So this is this graphing website I mentioned to you all last time. So this is x squared in red there. Okay, so we see it has that general shape that I drew. You know, their picture is much nicer, obviously. It's drawn by a computer. Here's x cubed. Okay, so here we see x cubed. What's the major difference? Definitely x cubed is like skinnier in a way, right? It's like growing faster, right? It's growing, meaning that, you know, like for instance, the point, where's the point? 2, 4, right there is on the red function x squared, whereas the number 2 for this function is all the way up at 8 already, right? So it's growing much faster. But also, maybe more importantly, the x cubed graph goes into the negative values, into the negative y values, okay? Goes into the negative y values, whereas the x squared function does not. The legs point in opposite directions, right? For x squared, they're both pointing up. For x cubed, one's pointing up and one's pointing down. What about x to the 4th? So let me get rid of these for a moment. X to the 4th is, again, both legs are pointing up, and it's growing much faster than the x squared graph if I put that one back up, right? By the time this x to the 4th graph hits 2, the number 2, it's going to be all the way up at 16, right? I'd have to scoot up to find it. 2, 16, somewhere around there. Oop, if it would let me. You saw it. There it is. I need to just graph the point. But anyways, you get it. It's growing much, much faster, much faster. But we do see that both legs are pointing up. So that's a similarity it has with the x squared graph, that both legs are pointing in the same direction. And when I say legs, I'm referring to this part and this part, or for the green function, this part and this part. So what about x to the 5th? So here's an x to the 5th graph, and you see it looks very similar to x cubed. Change its color to make it more. So it looks very similar to the x cubed graph in that the legs are pointing opposite directions. So what would we expect if I went to x to the 6th and x to the 7th, etc., etc. So okay, what does the exponent on x tell us about the graph? Let's say for f of x equal to x to the n, both legs of the graph point in the same, now I'm not going to say point up, because I can flip the graph completely over by putting a negative out front. So I'm going to be a little bit more generic here in my statement and say both legs of the graph point in the same direction. You'll see why later, why it's important to make that distinction. When n is what? Taylor, what has to happen to n for both of the legs of the graph to point in the same direction?
Do
So think about which one of these has the legs of the graph pointing in the same direction?
is it the red one?
Yeah, the red and the green one, right?
Mm-hmm.
And what is distinct about their exponents 2 and 4 versus these exponents 3 and 5?
They're even.
Exactly. Yes, they're even. They're even. That's it. So we'll say for some function f of x equals x to the n, both legs of the graph point in the same direction when n is even. When n is even. The legs point in opposite directions. The legs point in opposite, like up, down, or down, up, in opposite directions when n is odd. So the nice thing is, like, we're moving to a place where you're gonna be responsible for graphing a greater class of functions than you maybe ever graphed before. But the thing is that there's these rules that are gonna govern like entire chunks of these functions. So it's not like as you're learning this, you're gonna have to learn a new graph for x squared, a new graph for x cubed, x to the 4th, x to the 5th, x to the 6th, like on and on. What I'm saying is they all fall into like these two categories where they're either shaped like, both legs pointing in the same direction or in opposite direction, right? They're all falling into these two distinct categories, and you can use that to your advantage. So now if I say sketch a graph of x to the 5th, you can do it. You can say, I remember what x cubed looks like. It's like this kind of weird, curve shape here. So I'll just do that, but I'll make it a bit steeper to reflect that it's x to the 5th, so it should be steeper than x cubed. All right, let's continue on with, example 1's gonna be like a really long example. D, let's sketch a graph of f of x equals square root of x. Square root of x. Okay. By the way, I didn't explicitly write this down. The functions f of x equals x to the n, where n is like a whole number, like 1, 2, 3, 4, 5, like the ones we just looked at. These are called power functions. Just because they have a nice whole number power. That's it. So if you go look in the text for, there's actually a really nice table on page 202 that basically sums up everything I'm going to tell you today on page 202, and you'll see these categories as they describe them they call them power functions. So just so you know, that's just I won't call them that much. It's just another way to call them. All right, f of x equals square root of x. Okay, let's get straight into it. Make my table right here. So I've got x. Oops. Was I doing this in red before? Oh well. X and f of x. If I choose the same values, let's just naively choose the same values, 0, 1, 2. All right. What's the square root of -2? Well, that's getting into complex numbers, which we've studied, but we're not graphing, right? We're not graphing complex valued functions, even though that would be a lot of fun, but we're not doing that. We're graphing real valued functions, so that means undefined. You cannot plug, for our functions, you cannot plug negative values into a square root, or any even root for that matter. -1, similarly, undefined. Okay, so those were bad choices, right? Those were bad choices. What about square root of 0? That's fine. That's 0. Square root of 1. That's fine. That's 1. Square root of 1 is 1. Square root of 2 is, well, it's square root of 2, which is like some, decimal number, right? So these are bad choices overall. Like 0 and 1 are okay, but the other 3 numbers are bad choices. The first 2 are bad choices because they're just straight up not useful at all. They're undefined. Though they do tell us something, but we can do better for our table of values here. Let's say we pick x and f of x to be, or rather we pick the x values. First of all, we're going to start at 0 and we're going to go into the positives. We're going to take 1 as well because 1 was fine. What would be the next number that you think would be a good choice? Makira, what do you think if we're plugging into a square root function, what would be a good choice of number here?
Maybe 4.
Yeah, good. Exactly. Like square numbers, right? Perfect square numbers, and then maybe 9, right? And let's keep it at that because then they start to get a lot bigger, and I don't want to have to graph like 16, right? So I think these 4 will be okay. So square root of 0 is 0, square root of 1 is 1. Already said those. Square root of 4 is 2, and square root of 9 is 3. So when you're working with these, when you're building tables of values with these new functions, sometimes you have to play with the input values you're giving it to figure out what's going to be the best. When I say the best, I mean what's the easiest to graph, right? So here we go. No, I did not need all of that, but that's okay. So here's x and y. So I need a fairly long x-axis because I'm going out to 9. So make these tick marks kind of small. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's fine. Now for the y values, I only have to go up to 3. 1, 2, 3. So some things to notice here. I cannot plug in negative x values into this function. That means we should never see the function going over here. This is undefined territory. Because remember, we talked about the domain for this function. The domain for this function is supposed to be 0 to infinity, right? How do you represent 0 to infinity if they're x values? Well, that's the right-hand side of the coordinate plane where x is positive, right? Now, also, notice here that when I took the square root of the numbers, I'm not taking the plus or minus thing, right? Remember that, like, if I gave you an equation, I said solve this equation, x squared equals 4. Then the appropriate response would be to say square root of x, or rather square root both sides, right? And you get x is equal to plus or minus square root of 4, which is just 2. Okay, 2 answers here. 2 answers, right? But remember that we're not dealing with an equation, we're dealing with a function. So we have to agree all together to only pick one output value because the definition of a function says that one input, or this input, should only go to one output, right? You cannot have this input going to 2 different outputs, like a 2 and a -2. So we all collectively agree to just take the positive one, the positive value, the 2, instead of the -2, okay? And that's to maintain the idea that this thing is supposed to be a function and thus should behave as a function should behave. So since we're only taking the positive outputs, we will never go down here into the negative y values either. So here's what I'm going to say. since we are only taking positive outputs, we will not go into the negatives for y. Quadrants, and whereas y negative, well, quadrant 3 and 4. We were already not allowed in quadrant 3, right? But specifically also now quadrant 4 is not allowed. So we're not going into quadrant 3 or quadrant 4, which is, this is quadrant 3, so we're not going here, and we're also not going over here into quadrant 4. So all that to say, this function, this square root of x function, is stuffed into this first quadrant, which you can see from these numbers that I haven't graphed yet, right? So now if I graph them, and I've used all these, I guess I'll graph it in blue since I've used red and green to denote the places we're not going. The first point is 0, 0. The second point is 1, 1. The third point, let's get this graph right. It should be x is 4. So x is 4 and y is 2. So there's that point. The next one is x is 9 all the way out here and up at 3. All right, so it's like that. There it is. There it is. It's no coincidence that it looks like a sideways parabola. We'll talk more about that when we talk about inverse functions, but it's no coincidence that it very much looks like half of a sideways. Like if you took a parabola and rotated it like that, it looks very much like a sideways. It is a sideways parabola. It's just with half of it removed. Okay, so that's the general graph of square root of x. It's going to be this little half curve thing. Let's look at a odd root. So remember that this is technically like a little 2 in the square root. So I would call this an even indexed root. Okay. Let's look at an odd indexed root. So part E, f of x equals cube root of x. Now this time we can put in negatives into this, right? If you recall, negatives under odd roots were no problem. It's just negatives under even roots that are not allowed. So now I know that I can put negative values, but I've already learned that 2 was not a good choice for the square root because 2 was not a perfect square number. So we used perfect square numbers, right? 4 and 9 in particular were what we added to our table here. What are some perfect cube numbers I could use? Well, definitely 0 is going to be there, 0 is going to be there, 1 is going to be there, and -1 is going to be there as well, because negatives are okay, and 0s and 1s are always good numbers to start with when you're trying to graph something new. So let's see, Kimberly, what would be the next perfect cube number that would be, excuse me, a good choice to plug in as an input? So let me give you a hint. 1 cubed is 1. So what's 2 cubed?
8.
Yes, so that's going to be the next input we want. And similarly, we're going to want a -8 back here. Thank you. So again, negatives are okay. Negatives are okay. And where is the 8 coming from? The 8 is coming from the fact that I know 8 and -8 are perfect cube numbers. Thus, they fit very nicely and will give me whole number outputs, very nice outputs in a cube root function. They are perfect cube numbers. So they are good choices to plug in to a cube root function. And why do I say that? Well, because cube root of 8 is a nice whole 2. Cube root of -8 is a nice whole -2. Or it's not a whole number, it's an integer, but it's not fractional. That's the point, right? It's not a decimal, right? We can actually graph that very easily. Cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. So let's graph these. So we are not restricted here. Note that there is no domain restriction for this function. You can plug in whatever you want into this function. Like the square root function, there is a restriction. You cannot plug in negatives. And more than that, you cannot get out negatives, right? You can't give it negatives and you can't get negatives out of this the square root function. Cube root of x, though, is much more inclusive. It says you can give negative values, and not only that, it'll output negative values. So how is that reflected in our graph? Well, let me get my x-axis going here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then my y values are only ranging from 2 to -2. So say 1, 2, and 1, 2. All right, so x is -8 all the way over here. Y is -2. There's that point. -1, -1 is right there. 0, 0, that's easy to find. That's right there. And now it's going to be kind of mirrored over into this first quadrant. 1, 1 is there, and 8, 2 is all the way over here. So it's like that. Very much like a sort of sideways x cubed graph. Again, that's no coincidence, but I want to just kind of put a pin in that idea, and we'll get back to it in section 2.8, I believe it is, when we talk about inverse functions. Okay, so there it is. That's the general shape of a cubic graph. Not a cubic graph, I'm sorry, a cube root graph. The general shape of a cubic graph is that x cubed one we did before. This is similar to it, it's just on its side, right? So this is the general shape of a cube root graph. Now, let's, like we did for part C a second ago, make some observations Oh, one second. Let me make sure. Okay, make some observations about the graphs in parts or the D and E. In particular, here's the question. So the last question was, what does the exponent on x tell us about the graph? Now, I could write all of these roots as things with x with a fractional exponent, like x to the 1/3, if you recall from section 0.4. But let's just leave it in square root or root form, and let's call that number an index. What does the index tell us about the graph? So to answer this, so we'll have that question in mind. We'll go to Desmos and play with some differently indexed functions. And remember, when I say index, I'm talking about the little number that's written next to the root. You'll see in these examples we're going to do. And if you have a good feeling about what's going on, you should probably know it's going to have something to do with them being even and odd. So let me get rid of, I'm just going to get rid of all these. All right, let's say, oh, hang on, x. Okay, let's make it red. Okay, so there's the square root of x. That was part D. Square root of x, you see, it's only in the first quadrant. It's not going into the negative x values, and it's not going into the negative y values. Now, how do I do cube root of x? One second, I gotta remember how this works. I would usually just graph them with, there it is. Okay. So now I can type in that index right there. So I'll type a 3, and then, so here's the cube root of x. Why did it make it red again? There we go. Okay, so we see the cube root of x there. traveling into the negative values, right? Into the negative x values, and in fact outputting negative y values. Okay, let's look at the fourth root of x. Sorry, here we go. Normally it changes. There we go. Okay. Let's get rid of that odd function. Okay, now I'm gonna put both of these back. So remember that the square root of x, its index is technically a 2. There's technically a little 2. It's suppressed. It's a suppressed notation, right? But technically there is a 2 there. So these are the red and green are the two even functions. No, let me say it this way. They're the two even indexed root functions. That's the most appropriate way to describe them there. And if I did another one, another even one, function 6, their even root, and let's make it purple. We see that they're all behaving the same way. It's just as we increase the exponent, it's getting steeper and steeper. It's growing faster in the x direction, so it's like it's flattening out more. It's like flattening out more. See, we can really see it if we zoom in a bit more. The purple one, the sixth root of x, is much flatter and growing faster to the right than the square root of x or the fourth root of x. Okay, so we see they're all similar. These even indexed root functions all have the same domain issue where you cannot give them negative values, and in fact, they will not give out negative values. All right, now let's put the odd root functions up here so we get some feel for those. Fifth root of x. And let's do another one, and then I'll adjust their color. Let's do seventh root of x. Now just make this orange since it's less color. Okay. So, where is the, okay, zoom in a bit so we can see them all. So we've got the cube root of x, which is the blue one, the fifth root of x, which is the orange one, and the seventh root of x, which is the black one, and they're all sort of behaving the same way. They all can take in negative values and can give out negative values, in contrast to the even root ones, which cannot do that. All right. So how can we say that here? How can we write that down nicely? What does the index tell us about the graph? So for a function, f of x equals nth root of x, so that's an n in the index position. I'm going to say this, but there's a stipulation with this that is, if you negate the square root of x function, it can flip over and stuff, but this is fine. Yeah. Okay. The graph stays in quadrant 1 if n is even, right? That's the ones we saw there. And with the square root, the fourth root, and the sixth root, they all stayed in quadrant 1. And the graph goes into quadrant 1 and 3 if n is odd. So again, it's like the same thing. They have the same general shape. They have the same general shape. All the odd ones are going to have the same general shape as all the other odd ones, and all the even ones are going to have the same general shape as all the other even ones. Okay. let me see, what else do I want to do? We need to talk about reciprocal functions too, but first let me go to the homework and do a couple homework questions. Just things that the homework likes to ask that I want to make sure we're all on the same page about. So here are some homework questions. And then next time what we'll do is we'll finish. There's one more category of graphs we need to talk about, which is the 1/x stuff. And that will conclude section 2.2. But for today, I'd like to conclude with some of these questions from the homework that you may come across that I didn't explicitly talk about so far in the lecture. Here's a question. If f of 8 is equal to 12, then the point 8 comma blank is on the graph of f. It's on the graph. Dang, it just started pouring here. I bet you my Wi-Fi is going to go out soon. All right, let's try to finish this while I still have power, because it's starting to storm here pretty bad. Okay, so if f of 8 equals 12, then the point 8 comma blank is on the graph of f. Let's see, Nikita, what do you think the solution, what's the blank supposed to be here? If input is 8, gives an output of 12, then that corresponds to the coordinate point 8 comma. Okay, Makira, any ideas?
What was your question?
So what would this blank correspond to? So if the input is 8 and the output is 12, then what's the corresponding coordinate point for that relationship? Input is 8, so the x value is 8 and the output is 12. So what's the y value supposed to be here on the graph of f? So if f of 8 equals 12, the input is 8 and the output is 12. Just like that.
Okay, I was confused. Sorry.
Yeah, you're probably thinking 12, but thought maybe that was too easy of an answer, but that is it. This is exactly, when we say f of 8 equals 12, that literally means for whatever this function f is, like we don't know what it is, but that means that coordinate point somewhere out, I'll just make it right there, 8 comma 12 is on the graph of f. Maybe it's like something like, I don't know, like that or something, but that's the point. If we say f of 8 equals 12, then that means we could take that data and go graph that corresponding coordinate point on a Cartesian coordinate plane, with 8 being in the first position, typically represented by x, and 12 being in that second position, typically representing a y value on the vertical axis. Let's see, what else does WebAssign give you? Any weird ones? Nope, they ask you for this. Oh. Square root, no, not square root. The absolute value function. Let's talk about that real quick. I think we did something with it earlier. Let's quickly remind ourselves what that is. F of x equals absolute value of x. Remember that it takes in negatives and creates positives. So what I mean by that is if we pick -2, -1, 0, 1, and 2 as our sort of naive first choices here, those are going to be just fine. Absolute value of -2 is 2. Absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. If the input already starts off positive, it just copies them right over. That's what the absolute value function does. If it's negative, it makes them positive. Graph that on a plane. It's not going to go into the negative y values, right? The y values, the output values are always positive. I've got the point where x is -2, the output is +2, that's over here. Where x is -1, the output's +1. 0, 0, 1, 1, 2, 2. It's like got the same kind of feel as a parabola in that both legs are both pointing up like this, but it's more like a V, like very, very distinct straight line shapes there. Okay. Then they also ask you to graph, yeah, let me write this one down as well. The first question. Sometimes, WebAssign just, it asks the same things I'm asking you and telling you about. It just frames them in such a weird way. So they say, to graph the function f, we plot points x comma f of x, right? Like x comma y, x comma f of x in a coordinate plane. So to graph f of x equals x squared minus 2, we plot the points that look like x comma f of x, which is x squared minus 2. That's what the coordinate points are going to look like, though we really never describe them that way. But again, this is one of those WebAssign questions that's like, yeah. So the point 5 comma blank is on the graph of f. And what would that be? Taylor, what would that blank be? Like if you literally plugged in 5 into this function, what does it give you? Kimberly, what do you think? Oh, sorry, go ahead, Taylor.
You mean 5 of the x's, right?
Yeah, so the point 5 comma, and then what's the number that would correspond to 5 if you input it into this function?
I'm not really sure.
So you would say 5 squared minus 2.
So it should be 5 squared minus 2?
Yep, but what does that actually evaluate to?
I mean like 10 minus 2?
Well, if 5 squared is 25,
Or
right?
25 minus 2, yeah.
Yep, so 23. Yep. So this is just one of those examples of a question that WebAssign asks where they give you a function and they just ask for some random value, and they ask when they put a blank in the y value, which you would call the y value spot of the coordinate point, they're asking you to literally plug in x into the function. That's what that means. And that is the height of the graph f above the x-axis when x equals 5. That's one way they put it too. This is all true. It's just they just like to, I don't know, they're framing it slightly different. And then they ask you to graph, rather evaluate several different coordinate points for this graph, and then to sketch a graph of it, which we actually did do that, so that's fine. Okay. So I'm going to post the homework problems to mark for review for basically this entire chapter, because I went ahead and just found all of them that I want you guys to mark for review before you take exam 2, which you've got a while, but I'm just going to go ahead and give you all the problems. And also look at page 202 in the text in section 2.2. It's got a big old table there where they describe all the graphs. Basically, they sum up the entire section 2.2 on that one page there. There's one more thing we need to talk about, the vertical line test for functions. We'll finish that. So we'll talk. I need to write down what we're doing next time. So next time we'll talk about those rational functions and vertical line test. Okay.